So I've jotted down some thoughts here, key ideas. We started out looking at Newton's laws. Newton's first law, the law of inertia. Basically, if you want to summarize it, it says this: unbalanced forces must, you know what, let's capitalize that, must make an object, I'm looking for a word that begins with the letter A, accelerate. Must make the object accelerate. And it works backwards. If the object isn't accelerating, the forces must be balanced. This is what we used. We used this to find missing forces from a Freebody diagram. We used this to find missing forces. How? The most common one was, is this sinking into the ground like quicksand? Is this flying into the air like Superman? No? Well, then there must be a force pointing up. That was a direct consequence of Newton's first law. Okay. Another one, oh, is this object sitting still? Is it at a constant speed? Then there must be a force in the opposite direction, same size. That was Newton's first law. Newton's second law really says this: F net equals ma. It's the equation. That's all. It's F equals ma. It's really F net equals ma, but we've just said F equals ma. What does m stand for? Mass in kilograms. What does A stand for? Acceleration in meters per second squared. And as soon as I say that, acceleration, all of VF, VI, D, and T, all nice and fair game and available. But I think most of you did really well on that. And it's actually kind of a nice, pleasant review because we're about, well, 2/3 of the way through the year with report cards coming up so soon. So it's a nice way to already start refreshing our memory from stuff from before Christmas. Newton's third, how did I phrase it? Forces come in pairs. Really, we used this to identify forces in a free body diagram. What do I mean by that? We figured out, is it sinking to the ground like quicksand? Is it flying into like Superman? We said, okay, there's got to be an arrow pointing up. What force is that? Oh, the object is, the book on your binder is pushing down on the desk. What does the desk have to do? Push back up on the book. We called that the normal force. We called that the normal force. Or when you're walking, which way do you push with your feet? Backwards. What force pushes you forwards? Friction. We knew that there had to be a force pushing you forwards because you were accelerating forwards. That was Newton's first law. We figured out what it was by saying, oh, you push against the ground pushes back against you. Newton's third. Forces come in pairs. That's really why I spent so much time on those. Other key ideas. You should know the difference between mass and weight. The difference between mass and weight. Mass is measured in units, kilograms. Weight is measured in units, newtons. It's also called, that's what we typically call, weight is the force of gravity, mg. Okay? What's g on the Earth? Is g 9.8 everywhere in the universe? So your mass is constant, never changes in the universe. Sorry, that's a fib. We did note in the last unit when you started getting close to the speed of light, mass increased. We're not, again, I've been careful. We're ignoring all of Einstein's stuff in this unit. You'll notice any speeds and accelerations have not been anywhere near the speed of light. Okay, so removing that, your mass is constant anywhere in the universe. Your weight is location dependent. The further you go from the Earth, the weaker Earth's gravity gets, the lower your weight. Or on the moon, I think G on the moon was 1.6, so your weight would be whatever your mass in kilograms is times 1.6. So the difference between mass and weight, mass is mg, newtons, weight is, mass is kilograms, weight is mg, newtons. I said that totally backwards, but thankfully I caught it. Think about perhaps nice multiple choice questions here. For example, I could give you the mass of an object and I could say that we're on the moon, and then part A, this object on the moon. So let's suppose I said the object had a mass. Well, here, I'll make up a question. Example, an object with mass 55 kilograms is on the moon, and I might put in brackets G equals 1.6 newtons per kilogram. Wait a minute, isn't G measured in meters per second squared? It's an acceleration. Couldn't I also think about it as a force divided by a mass? Isn't that another way to think about acceleration? So newtons per kilogram, Courtney, it turns out, is also the same as meters per second squared. Then I could say, A, this object has a weight of 55 kilograms. B, this object has a mass of 55 times 1.6, 88 newtons. C, this object. So I could do stuff like this. This object has a mass of, weight of, and then I'd probably go 55 times 9.8, 545 newtons. I just realized this thing has a built-in calculator. That's kind of cool. Where is that weight on the Earth? D, this object has a weight of 88 newtons. Which of those is correct? D. Okay, so something like that. Or I might even do this algebraically without numbers. I might say it has a mass of M and a weight of, well, W, and then ask you some questions like that. So the difference between mass and weight, we're clear? We're okay? That's why I've gone so when someone said, oh, I weigh 80 kilograms. No, you don't. You weigh whatever 80 times 9.8 is in newtons. Freebody diagrams. This was the big tool that we've used. You can skip a freebody diagram if I talk about a net force. You can go straight to MA, because really what I've done, if I mention net force, that's my code sage to tell you I did the freebody diagram. I went winner minus loser, and I got the answer. Other key idea, this was our approach to solve anything. So, let's do some questions. Find the acceleration. We don't have a picture, Mr. Dewick. We will in a second. Sure. You know what? Let's get... hey, there, a nice generic blank one. You know what? I think I could even go like this. Copy. Hey, clever boy. Paste. Here's a diagram. Suppose I told you that M equals, you're all 17 kilograms. Let's suppose there was an F applied of 125 newtons. Let's suppose someone is pushing down with 25 newtons of force. Let's suppose that there is a coefficient of friction of 0.18. Find the acceleration. Okay? I've made this up. This might end up not being solvable. We might get a negative acceleration. If that's the case, oops, I apologize, but that's still good learning. This would be fair game. This is a fairly tough question. What makes this a fairly tough question, Matt, is the addition of an additional vertical force. But what does it want me to find, Matt? Is there more than one force in this picture here? This is a job for a good free body diagram. Okay? Just for giggles, I'm going to do the diagram here. You could label the diagram there, but just to show you how everything's put together. Hey, what are the forces acting on this mass? Get the obvious one. We would say, hey, you got gravity down. What else? Well, there's an additional force down. How big? 25 newtons. I would probably just draw it a tiny bit off to the side like that. What else? This is where we started using Newton's laws. Is it sinking into the ground like quicksand? Is it flying into it like Superman? So there has to be a force up, a normal force. In this case, is the normal force bigger, smaller, or the same size as mg? Courtney, why? Yes. What if that 25 had been pointing up? Then the normal force would be smaller. Okay? What else? There's an applied force. Boy, I hope this is going to accelerate. Is there friction, Drake? Say yes. How do I know? There's a coefficient of friction. Remember, you guys have really overcomplicated. This is a number that just describes how sticky the floor is. Or if it's not a floor, how sticky the two surfaces are. That's fairly slick. 0.18, probably linoleum and your socks, roughly. So do you slide forever on your kitchen floor in your socks? No. Can you slide though? Yeah. Okay. You wouldn't want, this is definitely not your sneakers and linoleum. That would have a fairly high coefficient of friction, probably closer to 0.6 or 0.7. Okay. Ice is close to 0. Magic perfect ice, Lydia, in our magic physics world would be exactly 0. Curling ice is really close. Curling ice is pretty good. Glue would have a coefficient of friction bigger than 1, because glue can hold its own weight and more stuff. Okay. So is there friction, Drake? Which way? Because if this is going to accelerate, it's going to accelerate to the right. So I would do that. And I think friction is smaller than the applied force, I hope, but we'll find out. Who's winning? Drake. Oh, sorry, Drake. What does this question want me to find? So this is when they want me to find either acceleration or when they want me to find what's mu. Hey, I don't know, what's mu with you? Usually my approach is going to be, I'm going to do a free body diagram, and I'm going to start going winner minus loser. So which way did you say this thing was accelerating? Who's winning? Yep. Who's losing? What does that always equal? You okay with that? F applied minus, Drake, how would I get the, he wants me to find A, how would I get the A by itself? How would I get the A by itself? Divide the M, nice. You awake? Okay. And then I could drop this friction down, or I could say to myself, self-friction equals what times what? Mu times the normal force, and none of you said mu mg. It often equals mu mg, but only if we have a boring question. So mu times the normal force. I don't know the normal force. Oh, but look. I can figure out the normal force from that right there. Let's find the normal force. It looks like everything up, Courtney murmured to herself, equals everything down. This one's nice. I got the Fn by itself already. Okay. If we've been lifting up, which I think is on one of your take-home quizzes, there we had to subtract to get the Fn. Well, there, the Fn got smaller. All of you right now are feeling that as your normal force. You're feeling the chair pushing you up. It's actually a combination of the chair and the ground through your shoes. You feel a little bit of both. Feel it right now. Concentrate on it. Feel it, okay? If you were feeling heavier, really what would be happening is there'd be an extra, this is right in Mr. Dewick, there'd be an extra force pushing up on you because there was an extra force pushing down on you. You ready, Ryland? I'm going to increase your normal force. You're going to feel heavier. Okay? Did his mass change? No. What changed? How hard the ground had to push up. Why did that change? I added an extra force pushing down right there. Okay? So then we could say it's going to be F applied plus mu, and then in brackets, mg plus 25 all over m. That's what I said. In brackets, minus, sorry, I'll make that a clear minus so you can see it never was a plus in the first place. Minus that there. Yeah, sloppy mistake, right? Are you all okay in typing those in? If you're not, now normally I would now plug in numbers, but we're cutting corners because it's after school. If you want to get out your calculators and follow along with me, let's go practice typing something. This is about as complicated as you're going to, the only thing that would be more complicated, Taylor, would be on the bottom M1 plus M2, or M1 plus M2 plus M3. So let's try typing this in. Taylor, is this a fraction? Is there more than one thing on the top? What you going to remember then, Courtney? So, bracket. F applied, 125. Minus mu, I said it was 0.18. 0.18 times. You may need to put a times there. You might be able to just open up a brand new bracket there and your calculator might clue in that's times. Hopefully I've gone on a rant about the usefulness of getting a good calculator. Hey, I wasn't kidding about that at the beginning of the year. And this is not the worst we're going to be dealing with by a long shot, believe me. And then I guess I can go M. What was M? 17. Oh yeah, I took your age for some reason. 17 times 9.8 plus 25. You could go 17 bracket, 9.8. Too many brackets to track. On my calculator, I only use brackets to group things, but to show times, I use times. It's way easier to read. I have to close off the normal force. I have to close off the top, divided by 17. And I get 5.32, that. Okay? If you didn't get that, either ask a neighbor to show you where you zigged on your calculator, because again, to me, calculator mistakes are throwing away easy marks. Am I right? Is that what you got? Okay, so just one more time. Don't clear your You didn't clear it, did you? No. Don't clear it. Pause, please. Don't clear it, don't clear it, don't clear it. By the way, this here is actually a pretty tough question. This is approaching Physics 12. However, listen close. You guys get the hint since you came here after school. On your test, I am going to give you one question like this where there's friction, where there's a mass, where there is an additional vertical force, and I ask you to find the acceleration. That additional vertical force could either be pointing down or it could be pointing up. That additional vertical force could either be pointing down or it could be pointing up. Okay? Some of you, yeah, okay. What else could I do with this same question? Well, to be honest, I could ask you to find mu. That's too tough for this question. And I'm going to assume that if you can find the acceleration for this, I'm going to assume that you could handle finding the acceleration for something without a vertical force, like that right there. Okay? So, instead, do I know how to do second squared on here? Home. Hey, there it is. Here's a picture. Oh, good gosh, I forgot to see if this can accelerate at 3 meters per second squared with a 50 newton. I think it can. Find the coefficient of friction if this object is accelerating to the right at 3.5 meters per second squared. Okay. What's this question asking me to find? Hey, what's mu? I don't know. What's mu with you? This time I'll do the free body diagram right on here. What are the how do I know I need a free body diagram? Mu is hidden in friction. There's no friction on this picture. I think I better do a free body diagram. Also, they didn't mention F net. What are the forces acting on this? Get the obvious one. What else? Normal force. This time the same size. Right, Court? Here's my applied force. Here's friction. I'm terrified. If I get, by the way, if we get a negative answer, then I've made up a question that's impossible, and I apologize. I'm trying to do a whole bunch of math in my head, more than I usually do. Who's winning? Applied. Who's losing? Okay. What do you say? Again, this is important. Who's winning? Applied. Who's losing? And friction contains a mu. This is where I kind of smile and I say, oh, I think I know where I might be going with this. So as an equation, I'll get F applied minus friction. What does winner minus loser always equal? MA. By the way, what if I had said steady speed or at rest? What would A be? 0, which would actually make this easier. I deliberately picked this one to be tougher, and then I'll show you, oh, if A was 0, not so bad. Friction is what times what? So my next line, I would go F applied minus mu times the normal force equals MA. And I smile because, hey, what's mu? I don't know what's mu with you. Although I don't like the minus sign. But we've done this dance before, haven't we? Yes? Easiest way to get rid of a negative, plus it to the other side. If it's in front of what you're trying to find, plus it to the other side. Oh, and at the same time, minus or plus any stuff from the other side back to here. If there had been a minus over here, I would have plussed it over to this side. Anyways, I think I get this. F applied minus MA equals mu Fm. Remember what I said to you? Hey, what if A was 0? What if we had steady speed or at rest? Then you'd just have that. I want to get the mu by itself. How would I get the mu by itself? Okay, so I'm going to get the applied force minus MA. Oh, thank goodness, this will actually give me an answer. Divided by the normal, I don't know the normal force. Oh, but look. I know the force is the same size as the normal force, and this one's a little cleaner than the one that Courtney did earlier. I think we can just say normal force has to be mg. But again, Ty, by doing that, we're using Newton's first law. We're saying it's not sinking to the ground like quicksand. It's not flying in the air like Superman. They have to be balanced. They must be balanced. So I could put a little mg there. Yeah. Again, normally I would write out my numbers, but this is a good chance for us to do calculator practice. Is this a fraction? Yeah. Is there more than one thing on the top? Yeah, brackets. Is there more than one thing on the bottom? Yeah, M and G, brackets around the bottom. If I want to go straight to my calculator, I would go like this. Bracket. By the way, let me emphasize, Kayla, on the test, please write the numbers for the next line. I'm just cutting corners because it's after school and you guys are tired and I want to get through as much as I can and talk about as I can. Okay? 50 minus 10 times, what did I say the acceleration was? 3.5? Close off the top, divided by bracket 10 times 9.8. This is going to be a pretty small answer, I think. Is it like ice-y? Oh, no, that's not bad. 0.15? Okay. That's about linoleum kitchen flourish. 0.153 would be a good place to round off to because there's a 0 after that, and that would be 3 sig figs. What are the units for mu? Are none. Okay? On the written section, I will be fussy on units. So you know what the last thing, Mateo, you should do before you hand the test in? Check your units, right? Yeah, all mu is a decimal ratio. The higher it is, the stickier the floor. Okay? What would the mu of gum be? Pretty high. You guys have come here after school. You get a hint. From the review, I like number 12. Except I'm just going to make up new numbers here. Please don't let me forget to talk about elevator questions. And then I'm going to talk about Atwood machines. You guys are good? Can you put it face down in the appropriate block? Not too bad, yes?
No, not too bad.
No surprises? But no telling anybody. He wrote the test early, so he's not crying, so it must have been okay. Although Connor's in there, and you know he's going to come back with... Right?
He's just getting confused on a question.
Oh, I can't imagine him ever overthinking things, ever. Okay. I like this question. I like this question. I like this question. I like it for a couple of reasons. First of all, if you haven't figured it out by now, I'm a little bit of a space nerd. I do dream of a Star Trek future. Sadly, I also think in terms of physics, it'll never happen. But I hope. Ask me sometime, not today, about the Fermi paradox. Let's change the weight of this rocket. How about let's make it a big rocket. How about 20,650 newtons on Earth? Let's make the force of propulsion a little bit bigger. You know what? Let's even do better than that, Mr. Dewick. Yeah, let's build a rocket. And let's find the velocity at the end of 65 seconds. A rocket which weighs that much on Earth is launched. The force of propulsion is that. Determine A, the mass of the rocket. Isn't the mass of the rocket 20,650? If this was the mass, what would you see there instead of an N? Kilograms. So Sage, is this the mass of the rocket? What did I give you? The weight. How can I find the mass of the rocket? What I've given you is mg. How can I get the m by itself? Divide by g. So the mass is going to be 2,650 divided by 9.8, which I can't do in my head. 20,000, no, sorry, 20,000. Did I say 2,000? 20,650 divided by 9.8. We had an over-under that you're going to get confused and bugged by one question and come back here all stressed.
Nope.
Okay, put it face down in the appropriate block. No surprises? No telling them any hints. This rocket weighs 2,107.1 kilos. Now, I'll be honest. If you said 2,100 kilos, I'd give that full marks. But I have a feeling I'm going to use this answer to find other stuff, so I'll carry a few extra sig figs, Courtney, to be more accurate. Really, what I would probably do is I would write that, and I would put an equal sign, and I would say 2,100 kilograms. Courtney, what's part B want me to find? Which way? What I'm really wanting you to imagine, Drake, is this rocket is like a meter off the ground. Why is that important? No normal force. Okay, it's not sitting on a surface. So, Ty, let's go for a rocket ship. Ty, what are the forces acting on this rocket? Get the obvious one. Is there a normal force? I said it's off the ground now. Let's imagine like a couple of meters off the ground. Right here, let's say. Okay? No. Which way is it accelerating? So there has to be a force, a bigger force pointing which way? What force is that? You know what? The fancy word for that is thrust. That's usually what they talk about with rockets. But yeah, for any rocket ship, you need a bigger force pointing up than you do have gravity down. Otherwise, you're having problems. Okay? You okay with that? Well, who's winning? Who's losing? You okay? Can I abbreviate propulsion with a P now? Yes? What does that always equal? You know what? I even did that already because I knew I wanted to get the A by itself. We've done that before as well. Okay. Boy, I'm kind of curious. I crunched some numbers. I suddenly realized A might be so big that astronauts wouldn't survive, and then I'd feel kind of guilty. 63,400 minus. Now, mg, I could go this mass times 9.8, or if I'm really clever, I can notice that mg is 20,650. That's what weight means. I'm going to do that. 20,000 650 divided by, and then I could divide by the mass. I could type that. You know what? I'm going to go divided by my answer button because I noticed that my last answer was that there. Ah. Yeah. That's a little more than 2 G's. That's doable. You wouldn't want to deal with that for like an hour. Because remember, how big is 1 G? 9.8, which is really close to what number? A nice round number. It's really close to 10. 20, it's about 2 G's. A little more than 2 G's. If you're wondering how I'm able to do these so fast, I just divide by 10, right? So 20.3. Okay. Then, are you guys okay? Part C, finding VF. VI would be 0. VF, don't know. T would be 65. Do you want me to, you know what? I see a few of you looking at me blankly. I'll get it started. I think I'd go like this. I've seen rocket ships. For any rocket ship, what's VI always? Yeah, I've watched them launch. I've never seen them take a running start, right? Okay. I wrote 20.3. Once again, I use my answer button, right? Is that okay? Elevator questions. Usually we ask about a scale reading. What are we really asking about? FN, right? I'm sure I shared all the joke with you, and I'll say it, get an FN clue, right? I mean, really, though, that's what we're talking about here. A scale measures in newtons. Now, if I just for giggles decide to ask you what the scale would read in kilograms, how do I go from newtons to kilograms here on Earth? You too. How do I go from newtons to kilograms? Divide by 9.8. That's how, and this is awkward because unfortunately I have to use the word scale twice. The scale on your scale, sorry, all that is it's newtons divided by 9.8, and that's calibrated for kilograms. That's all it is. Okay? Some thought experiments. If the elevator is accelerating up, the person feels heavier, lighter, the same. Convince me.
Because once you manipulate the equation, it's mg plus ma. So
What are the forces acting on this person? Get the obvious one. What else? Bigger, smaller, or the same size as mg?
going upwards.
I got to be fussy. If we're accelerating up,
Bigger.
what's my equation?
Fn minus mg.
Or the normal force, which again, remember, is what you all feel is your weight. I showed you the video of the little kid experiencing the changing normal force. I said to you, all an amusement park ride does, Kayla, is it mucks around with the normal force. I'm telling you, they're not changing mg. They're not God. They can't change the universe. What they can change is how hard the floor and the seat pushes up against you. We'll pay good money for that. So in this case, normally, that's your normal force, mg. Here, we're adding to it, this person feel heavier. What about if you're accelerating down? Feel lighter? What, and this is why I cut you off. What if you're going up at a constant speed? The same. Why? Because A would be 0, and you can see it. Well, if A was 0, that term would vanish, and you'd feel, no pun intended, your normal. Okay? Yeah, we need more words in the English language. Scales on scales and normal, normal. I know. Okay? But by the way, it's this little thought experiment right here and the fact that you can't tell if your elevator is at rest or moving at a constant speed. This is what got Einstein thinking about general relativity and saying, well, what if we accelerated up at 9.8 meters per second squared? You would feel like you were in free fall. You couldn't tell that there wasn't gravity. You would feel the earth pushing, you would feel your normal. And this is what got Einstein thinking, hey, maybe instead of gravity being a force, maybe it's actually space-time itself moving up against you. And Einstein really does argue that when you drop an apple, the apple doesn't fall to the earth. Space-time warps itself, and space of the apple and space of the earth meet in the middle. This is what got him thinking about all that. He said, you know what? I can think about it like an elevator. It's kind of cool. So if you were all smart, you'd come up with that too. Just saying. You saw that in Futurama?
Yeah.
Oh, that's where you get your science from?
Oh, yeah.
Okay. Let's do an actual question. Hey, elevator question. Copy. Paste. Come on, don't crash. Uh-oh, don't crash. Now I'm terrified. Because that was a pretty minuscule paste. It shouldn't take this long. I'm not going to touch anything. I don't dare touch anything. Come on, green bar. A little weird, but okay. By the way, did I remember to hit play? I did. Good. Okay, I'm going to nuke all this then because that just went wonky. Let's make the person, I don't know, 720 newtons. If the elevator has an acceleration of 4.3 meters per second squared down. No, I don't want that. I want superscript, Mr. Dewick. I want to be super. Now, some of you may be good enough that you can see the equation now, and if you've reached that point in your homework, I'm okay with it. You know what, Robbie, on the test, I'd take the 1 second to draw the free body diagram, right? So, hey, Robbie, here's the person. What are the forces acting on him? Get the obvious one. I totally agree. What else? Which way? Bigger, smaller, or the same size as mg? Gotta be. What's my equation going to be? This wants me to find the scale reading. Really, it wants me to find the normal force. You guys with me back there? Good, shut up. Here we go. Thanks, guys. That's on YouTube, too. Mr. Dewick telling students to shut up. You know I was only joking, right? Good, shut up. Oh, yeah, oh, man. I can just imagine the angry letters I'm going to get. I do get the odd email. They're usually complimentary, but sometimes they're mean. You ready? We've done this dance before, right? So I think we'd get this. The mg would drop down like a domino. The ma would be a minus. And do you mind, Robbie? I'm going to put the normal force over there by itself because that just looks prettier to me. What's mg? The most common mistake I see here. Did I give you the mass? How do you know instantly I didn't give you the mass? Because what's next to that 720? Newtons. Oh, you know what? That's mg. Great. Minus, did I give you the mass? Is that the mass? You could do that on a separate, like off in the margin somewhere, Mike, if you wanted to as well. But, you know, I might even just type that in one fell swoop because I'm that lazy. And then times the acceleration. 4.3. Mr. Dewick, it's down. Don't I need to do negative 4.3? Where did I include the negative? Yeah, in that arrow. That's the negative right there. I've got it in here. It's built in. So that's why I really like this draw a good free body diagram and then Zealand go winner minus loser. It really takes care of the minus minus. Is it a negative? It takes care of all of that for me. You okay? So, by the way, little warning, in about 5 minutes, I'm going to yell. Okay? Just letting you know. So I would go 720 minus 720 divided by 9.8 times 4.3. This should work. And they would feel a normal force of 404.1 newtons. What if, for a part B, I said, what does the scale read in kilograms? How do I go from newtons to kilograms? Yep. Just divide by the scale. If it was a kilogram scale, which really most of your scales are, I doubt any of you own a Newton scale, the scale would read that this person was 41.2 kilograms, as opposed to their original mass of 720 divided by 9.8, 73.5 kilograms. They'd feel almost half their weight. To be honest, if you were in this elevator and it accelerated like that, probably you would let out a shriek. Ah, this is far bigger than you'd be used to. Express elevators don't go this fast. I'll bet you the elevator is probably close to around that when it accelerates you down. Now, how many of you been on the elevator? Okay, when it goes down, do you feel like you're going to get thrown out of your seat? Yeah, notice you're not. Those straps could be gone and you're still perfectly safe. There is still plenty of force holding you to the chair. But it's a great illusion because none of you are used to that feeling. Okay, the classic is the Twilight Zone Tower of Terror. Anyone been on that one at Disneyland? Okay, that's a great one for physics. I'm pretty sure those seat belts, those lap belts, probably don't even need to be there. They're there to reassure customers or to make sure that someone can't stand up in terror, and now they've introduced a different force into the equation. Now because they could probably, if it's going down, jump higher than normal, and they might hit their head on the ceiling, and that's a lawsuit. But in terms of keeping you onto the bench, I doubt it's necessary. I doubt it's necessary. I need to go on there with something in my hands that's very lightweight so I can open my hands at the very top and see if it does go weightless for a split second. I don't know if it would. I'd have to try that. Do I need to do, what are the variations on the elevator question? Constant speed. If it's a steady speed, what's your acceleration? 0, makes it easier. Free fall. You probably all know this. If the elevator is in free fall, what will the scale read? 0, no normal force. That's, by the way, really the definition of apparent weightlessness. The astronauts in the ISS are not in 0 gravity. If the Earth can hold the moon with its gravity, I assure you the Earth can reach the ISS with its gravity, but they're in free fall, just like the OK Go video that I showed you as well. Okay? And if you watch the behind-the-scenes making of that video, it's really pretty intense. Yeah, I think it's the bassist or whatever has a panic attack on the first. It doesn't deal with. In the end, he really wasn't that all thrilled with that whole video, and I think he upchucked it more than a few times as well. Anyways, then we moved on to more than one mass. You know what? Probably I'll cap it at 2. Well, maybe 3 masses is like a bonus question or something, but like in terms of the main meat and potato, 2 masses. Because I figure if you can handle 2 masses, honestly, Kayla, you can handle 9 or 10. It's just more winners and losers, more winners and losers, more winners, more tensions, more tension cancels. Okay. So what do I mean by more than one mass? Well, first we have the famous Atwood machine. I'm going to ask, is there anybody who would like me to do an Atwood machine? I can. But if all of you are good with it, I don't mind passing because it's already getting a bit late. Want me to do an Atwood machine? Okay. I have no problem doing one. Hey, here's an Atwood machine. Move it to here. Can I flip this? That would really be cool if I could. Rotate. Look at that, I can. Let's put the heavier mass, because I think all the examples that I did with you, the bigger mass was on the right. There, this time, let's say we have this, okay? And let's make this 14 kilograms, and let's make this 8 kilograms. What am I going to ask you to find? You know what? I'm just going to say, find the tension. You can't yet. First, what you have to find is the acceleration of the whole thing. Then you can find an individual force like the tension. But how are we going to start this? What are we going to do first? What are the forces acting on this 14? Get the obvious one. Sorry, can you say it with authority? Get the obvious one? Is there more than one mass? Is there more than one mass in this question? Say yes with authority in your voice. Then Courtney, I'm going to label this one M1G. Courtney, what am I going to call the other one? M2. Why call them both M and make it confusing, right? What else? What you're feeling right now? And if you're looking for that as a stupid way to remember that, use that, right? I can't remember the force. I'm getting all tense. Oh, that's right. Is there a normal force here? No, because it's not sitting on a surface. What else? That's it for mass 1. Mass 2. Who's winning? Which way is the 8 kilogram mass going to accelerate? Up or down or not at all? Why? Because the 14 is bigger, heavier, winner. So my equation is going to look like this. Winner minus tension, okay? And Courtney, the reason this is a loser is because I've decided that anything that ends up pointing down on this side is going to be a winner plus. So that's why tension ends up being a loser. However, Renzo, this tension, although initially you might think it's a loser because it's pointing up like this guy, if you follow it, when it gets to this side, I think it ends up pointing down. You got to use your imagination a little bit, but it does, yes? You go, it ends up pointing down, yes? So it's going to be down, winner plus. And I think you get loser minus. Is that okay so far? Yeah. I'm desperately looking to see if it was someone that's here. I don't think so. Connor, my friend, do I have more than one mass over here? Yes. I have forces from more than one mass over here. Say yes again. Yes. Then I better have more than one mass over here. Bah! Here we go. Both barrels. That was a double barrel. I got Robbie, I got Gila. By the way, those of you that are in the different blocks, there's one person in each block that jumps. So it's Gila and that, but Robbie. It's great fun. I got Michael. It was great fun. Oh, sorry, YouTube. Sorry. Wait for it, though. You're awake now, right? Okay. Hey, and on that related note, how about we lose a little tension? Thank you, Mr. Dude, thank you. Did you time that? Yeah, that's actually, I was waiting for that to come. Okay. Figured I'd yell and then we'd lose tension. I feel great. Renzo, how would I get the A by itself? So it's going to be M1G minus M2G divided by M1 plus M2. Again, normally I would write out all these numbers. Sage, this is a great opportunity for us to practice with our calculators. Let's get them out. Renzo, is this a fraction? Is there more than one thing on the top? What will I remember? Is there more than one thing on the bottom? What will I remember? So I think I can go bracket M1, 14 times 9.8 minus 8 times 9.8, close bracket, divided by bracket 8 plus 14. By the way, on the bottom, since it's plussing, you could go 8 plus 14 or 14 plus 8. I always go M1 plus M2 because numerically that just makes sense to me, but whatever. What's the maximum acceleration that I could have? 9.8. What if the masses were identical? What would the acceleration be? 0. 2.672727, that there. Is that right? I hope, yes? All right, 2.67 meters per second squared. It's an acceleration. But, Renzo, that was not what this question asked me to find. What did this question ask me to find? What you were feeling after I yelled. Yes! To find tension, now I go look. Now, you know what? On the test, I think I did part A, find acceleration, and then part B, find the tension. But certainly in physics 12, I would have no problem just moving straight to part B and assuming that you'll clue in, oh, I got to do part A before I do part B. In other words, I'm introducing multi-step questions to you this year. Next year, though, I don't break them into steps. I just say, find me the final thing. Vikas is in my physics 12. I'll just find me whatever you need to find me, and I'll expect that you clue in that you need to go, oh, I need to find that, which can help me find that, which can help me find that, which will get me to there. Right? Remember the good old days? Yeah, you're looking at this and just going, boy, how did I not get an A last year? Okay, here we go.
I was close.
Oh, you got to do your homework. Oh, it slipped out, sorry. So, find the tension. Which mass do you want to use, Renzo, to find tension? You want to use M1? Okay. I might have chosen to use M2, but M1 still works. Which way is M1 accelerating? Up or down? Yeah.
You said you would have chosen M2. Why would you have chosen M2?
Patience, young grasshopper. Which way is mass 1 accelerating? Up or down? So who's winning? Which force is winning? Oh, yeah, didn't mean to erase that. So we would have this, M1G minus tension equals, I'm looking at one force, one mass, sorry, not one force, one mass, so it's going to be M1A. Robbie, in answer to your question, I know Michael said it, I might have chosen this just because tension's a winner, and it would be slightly easier to get the T by itself, but only slightly. I'll be honest, in grade 12, by then I figured they're good enough at the formula manipulation that I just don't care. I expect even complicated equations are just the same amount of work to get the whatever by itself. Again, because you look at what we've been doing in orbits and things, how you're rewriting that. It's pretty old hat now, I hope, yes? I want to find tension. You know what? I think I would plus that there, Renzo, and minus that there. And I would get tension equals, the M1G would drop down, there'd be a minus M1A equals tension, but I move the tension over to the left-hand side because I like it there. Is that all right? Yeah. Do I know M1? Yep. Do I know G? Yep. Minus, do I know M1? Yep. Do I know the acceleration? Yep. Could I find the tension? I'll assume you can type that in. Just remember, tension is measured in newtons. He already has, thanks. 2 more multi-mass questions, and then I'll take individual questions or we'll wrap it up. Okay? I'll email it to you, but then you'll get the whole copy. I'll email it to you as a PDF. Because for me to print right now involves a bunch of steps and I don't want to interrupt stuff. Okay? Well, the only other 2 mass questions that we did was mass hanging over a cliff. Like, here, mass hanging over a cliff. I want one with friction. I want one with friction. Yeah, I stole these from all over the place. What, you like the choo-choo trains here? Here what we would probably find is the tension right there, which is surprisingly the 2 masses. Who's winning? We would need some kind of an applied force from the engine. I need to add more stuff. Show me something hanging over 3 masses. Yeah, I know. Oh, here. That'll work. Oh, there's the same one. I just flipped it, apparently. Let's use that one. Okay. Let's stick some numbers on here. Let's say that there is Mu equals 0.53. Kayla, same as I mentioned, I'll email this out, okay? I should be done in about 15 or less, I hope. Let's make this mass here 6.3 kilograms. And I'm going to make this one really dense and heavy, so I'm going to make this 12 kilograms. First thing you need to realize is there any way that if you had this set up and then you walked away, that this would magically start crawling to the right and lifting this up? And this may seem obvious, but kids are having a tough time wrapping their brain around it, because what bothers me is when I say, who's winning? Well, let's label our forces. What are the forces acting on this? Here is M1G, tension, M2G, normal force number 1, tension. Oh, and I guess friction force number 1. Who's winning? It's got to be that or nothing. It's either a tie at rest 0 acceleration, or that's pulling everything down. So let's start out with down and to the left as the winner. I think the one that I gave you on your quiz was down and to the right. I don't mind flipping a diagram. This is good practice for us. So our equation would look like this. M1G minus tension plus tension minus friction force 1 equals, Connor, have I used forces from more than one mass? Connor, have I used forces from more than one mass? Connor, have I used forces from more than one mass? Yes? Yes? So I better have more than one mass on the right-hand side. Were you wrong in your initial no? Yeah, but I say to you, ease your tension. How would I get the A by itself? Okay. The M1G would drop down, the minus friction would drop down, and I'll divide by both of those. Is that okay? Friction is what? Oh, it's friction force number 1. Sorry. Mr. Duick, call it, how about 2 and friction force number 2, because I called it mass 2. That would be silly notation, wouldn't it? Friction force number 2. Friction is what times what? I don't know the normal force. Oh, but look. Now, by the way, ready? Preview of physics 12. I might add an extra force pushing down. Now the normal force isn't mg. I've snuck that in this year anyhow. Or I could have an extra force lifting up. Now the normal force isn't mg. The real preview of physics 12 is we start to do stuff on hillsides, on angles, so that gravity no longer acts straight down. Gravity acts down the hill. Okay? And as Vikas remembers, we have mg parallel, mg perpendicular. Mg parallel, 2 lines, is an mg perpendicular. Of course it is. Okay, here we go. Dumb, stupid ways to remember some trig. We get triggy with it in physics 12. Oh, they like that one. Okay. Note to self. M1, 12. Don't get your masses mixed up. G, 9.8. Don't forget the mass and the G. The number of times this young lady who's just left, whose name I won't say out loud on the video, earlier today, why am I getting the wrong answer? You forgot the 9.8. You had the mass. You forgot it's mg. I've seen other people, why am I getting the wrong answer? You've got the 9.8, but you forgot the m. Okay? Minus mu 0.53 times the normal force. I don't know the normal force. Oh, but look. It's going to be m2 times g all over 12 plus 6.3. You need to make sure you're okay with typing that in. I'll do it real quick here. Let me uncover the work. It would be bracket 12 times 9.8 minus 0.53 times 6.3 times 9.8. Close off the top, divided by bracket 12 plus 6.3. I should get less than 9.8. I do, so at least I'm in the ballpark. Okay. Hey, you want some more rough rules of thumb? The masses are roughly 12 and 6, roughly. Is 6 half of 12? Is 4.6 roughly half of 9.8? Again, I figured the answer was going to be around there somewhere. There's all sorts of tricks of the trade you can bring in here if you keep your eyes open and just look for patterns. Okay. What else would I ask with this? I might say, part B, find the tension. Which mass would be the easier, the nicer, the less yucky mass to find the tension with? This one? I'd probably do that one just because of the effort, the fact that I would have to recalculate friction. Where here, this is more plug and chug. Although tension is a loser, it's so easy to get the T by itself. We've done this dance before. I'd probably go with that. Okay? The only other thing, Ryan, just before you go, the only other thing that I could do is I could ask you to get the mu by itself. I'm not going to give you one that tough on your test. Okay? If I'm going to give you a fine mu, it's going to be a single mass on level ground. So folks, that's the tutorial. Any questions, anything else you're wondering about? If you can stick around for 5 minutes, I can print this up. If you have to go, I'll email it out. I will. It's not going to get out for about another hour and a half, though, so I've got to upload the video. Any specific questions? That help? I hope? Okay. Hopefully, we were connecting dots that were already there. I've thrown a lot at you, but hopefully it was, oh, okay, now, that's what I was missing. All right, let me pause the video.